In this lesson, we're going to be talking about how we can find the confidence intervals for the population mean. This is using small samples taken from a normal population of unknown variance. Now, for a sample of size n, where n is small such that n is less than 30, taken from a normal population of unknown variance, a confidence interval for the population mean mu is given by x bar minus t of s over root n and x bar plus t of s over root n, where x bar is the sample mean, s is the unbiased estimate of the population standard deviation, and t is the critical value of the t distribution with n minus 1 degrees of freedom at the chosen significance level. So we want to look at an example where we can calculate confidence intervals of this kind. So here's the question. It says, a machine produces metal discs whose diameters have a normal distribution. The mean of this distribution is intended to be 10 centimeters. Accuracy is checked by measuring the diameters of a random sample of 6 discs. The diameters in centimeters are as follows. So we have 10.03, 10.02, 9.98, 10.06, 10.08, and 10.01. So they say calculate a 99% confidence interval for the mean diameter of all discs produced by the machine. Alright, so here we want to calculate the confidence interval. That's a 99% confidence interval. And for the calculation, we shall need to know the sample mean from the given data, and we shall also need to know the sample variance. So first of all, I'm going to enter the data that we have here into our calculator. Alright, so I'll go to stats mode. So that's mode, then option 3, then option 1. Then I'm going to enter this data here. So we have 10.03, enter. We have 10.02, 10.02 here, and enter. We have 9.98, so that's 9.98, enter. We have 10.06, enter. We have 10.08, enter. And we have 10.01, enter. So we have 6 entries here. So now we are going to need the sum of squares. So I'll go shift and start, and I go to option 3 for sum. So the sum of squares here is coming out as 603.6118. So I'll write that down. So sum of squares is equal to 603.6118. And we shall also need the sum of the numbers. So that's shift 1, option 3, and option 2. And we get 60.18. So the sum of the numbers is 60.18. Alright, so we can now calculate the sample mean x bar, which is, in this case, 60.18, and that's divided by n, which is 6. So we're going to divide this. So let's just say divided by 6 here. So we get 10.03 for the sample mean. So that's 10.03. And then for the unbiased estimate for the population variance, s squared, we find it by 1 over, in this case, since we have 6 entries, so it will be 1 over n minus 1, which is 1 over 5. And that's times the sum of squares, which is 603.6118. And that's minus the sum of the numbers squared, so that's 60.18 squared. And that's going to be over 6, which is n. So we're going to compute this again. So that's a fifth, and that's of 603.6118, and that's minus, and here we'll be having 60.18 squared, and that's over 6, close bracket, and we are going to get 1.28 times 10 to the power minus 3, which basically is 0.00128. So this is what we have for the unbiased estimate of the population variance. Alright, so with this, we can now find the 99% confidence interval. But before we do, we also need to find the critical t-value. Alright, so we can consider the t-distribution curve to be like this. And since it's a 99% confidence interval, it means this region here is 99% of the distribution. Okay, so if this is 99%, then the tails will be having 0.5% each. So this is 0.5% and this is 0.5%. So for the critical t-value, we are considering the area to the left of it, which is less than t. So that's 99% plus 0.5%, which is 99.5%. So here we are looking for the t-value at 5 degrees of freedom. Since we have 6 entries, the degrees of freedom will be n-1, and it's for 0.995 from 99.5%. So we're going to go to the tables for that. So under 5 degrees of freedom and 0.995, we find this value here, which is 4.032. So we have 4.032. So we can now write down the confidence interval. That's going to be found by x bar, which is 10.03, and that's plus or minus, and the critical t-value here is 4.032, and it's going to be times s over root n. S is the square root of s squared, the unbiased estimate for the population variance, over root n. So I'll just say the square root of 0.00128 over n. N in this case is 6, so like this. So we're going to get our limits here. Let's do the calculation quickly. So that's going to be 10.03 minus 4.032, and it's times the square root of 0.00128, and that's over 6. And we are going to get 9.97 for the lower limit, so that's 9.97. And then for the upper limit, I'm going to put a plus here, and we are going to get 10.123 SF. So we have 10.1. So this is what we'll be getting for the confidence intervals. Now let's go on to the next part. The question says, deduce a 99% confidence interval for the mean circumference of all discs produced by the machine. So on part A, what we got was the confidence interval for the diameters of the disc. That's what we got to be 9.97 and 10.9. And here they want us to deduce a 99% confidence interval for the mean circumference of all the discs. So we know that to calculate the circumference, we do that by pi times the diameter. And remember, we already have the confidence intervals for the diameters. So what we're going to do for the confidence intervals of the circumference is we're going to multiply the limits of the confidence intervals we got above by pi. So I'll do that. Here we had done the calculation for minus, and we got that to be 9.97 going. So I'll multiply by pi, so that's times, then shift pi, and I'll get 31.3. So that's the lower limit, 31.3. And for the upper limit, let's see if we still have it stored. Okay, let me just put a plus back on it. Delete plus. Okay, so we multiply this by pi and we get 31.7. So we have 31.7. So what we have now is the confidence interval for the circumference of all the discs. And that's how we do it.